Just a little brief discussion here about the vector operation of a cross product. I talked a little bit about it in class last time, but here's an overview of the cross product. The cross product between two vectors, v and w, yields a vector that's perpendicular to both vector v and vector w. So if you have a vector in space, v and w, the cross product makes a right angle to both v and w. So remember that the dot product was a scalar. The cross product is a vector. The way we compute a cross product is to write it as a 3x3 determinant, where the first row is the unit basis vectors I, j, and k. The second row are the components of vector v, or the first vector written in the cross product notation. And the third row are the components of the vector w, written in of the second vector in the cross product notation. And I'll compute this 3x3 determinant by expanding it in terms of 2x2 determinants. To get these 2x2 determinants in the I direction, you just cover up the I column and write the remaining 2x2 determinant here, a2, b3, a3, b2. And then the same goes for the other ones. For the j component, you cover up the j column, and then the resulting 2x2 determinant would be here. And then finally cover up the k column and then write the 2x2 determinant. We compute the 2x2 determinants by multiplying the forward diagonal numbers together, multiply the reverse diagonal numbers together, and subtract forward diagonal minus the reverse diagonal. Forward diagonal minus reverse, forward diagonal minus reverse. The signs alternate. The first one's positive, then minus for the j component, plus for the k component. And that gives you a vector. So let's compute one here. We'll compute three of them. I've got vector v cross w. So we'll do the determinant I, j, k. Vector v has 1, 2, 3. W is negative 2, 0, 1. So our little cofactor expansion would look like 2, 0, 3, 1 in the I direction, minus 1, 3, negative 2, 1 in the j direction, plus 1, 2, negative 2, 0 in the k direction. And now when we do the products, we get 2 minus 0 1 minus a negative 6 in the j direction, plus 0 minus a negative 4. So altogether we have 2i minus 7j plus 4k. Now remember we said that this vector is orthogonal to both v and w. Which means that their dot products should be 0. So let's make a quick check. Let's take the dot product between what we got as our cross product vector and vector v. And so we get 2 times 1 plus negative 7 times 2 plus 4 times 3. So we have 2 minus 14 is a negative 12 plus 12 is 0. Let's do it again. Let's take the dot product between this vector and vector w, negative 2, 0, 1. And we get 2 times negative 2 plus negative 7 times 0 plus 4 times 1. So the middle term 0, negative 4 in front, 4 in the back, booyah. We've got the cross product correctly. Now we're going to compute V cross W. So we set up the same 3 by 3 determinant, but swap those two rows. Write the components of W first. And so let's expand this in terms of the 2 by 2 determinants. 0, 2, 1, 3, I minus negative 2, 1, 1, 3, J plus negative 2, 0, 1, 2, K. Now let's go down our diagonals. We have 0 minus 2, I minus negative 6 minus 1, J plus negative 4 minus 0, K. And so we get minus 2I plus 7J minus 4K. So notice that that's opposite in sign as what we got in part A. So in general, vector V cross W will always be the opposite of vector W cross V. Vectors in opposite directions. Next cool thing is what happens when you cross a vector with itself. So let's compute this. Vector V have the components 1, 2, 3. And then when we write that out, we'll have 2, 3, 2, 3 here in the I direction, minus 1, 3, 1, 3 in the J direction, plus 1, 2, 1, 2 in the K direction. So each of the components, looky here, forward diagonal minus reverse diagonal, is going to give you 0. So this is a vector, so we write it as the 0 vector. Anytime you cross a vector with itself, you'll get the 0 vector. So V cross V is 0 for all vectors. V cross W is the opposite of W cross V. The cross product gives a vector perpendicular to both V and W, so when you take the cross product and dot it with either V or W, you should get 0, not the 0 vector, the 0 scalar. There is a distributive property through addition. U cross V plus W is U cross V plus U cross W. The law of signs gives us that the magnitude of V cross W is equal to the magnitude of V times the magnitude of W times the sine of angle theta. So we've got yet another formula to find the measure of the angle between two vectors. The dot product's much quicker, but the sign works as well. V cross W is the area of a parallelogram whose sides are V and W. So there they are. And since a triangle is 1/2 the area of a parallelogram, 1/2 of V cross W gives you the area of the triangle whose sides are V and W. Something that we call the scalar triple product, which was the cross product of two vectors dotted with a third one, we should probably put that in absolute value to make sure we get a positive number. That scalar triple product is the volume of a parallelepiped, or a box that's been sat on, whose edges are vectors V, U, and W. So let's use the cross product to find the area of a triangle. So remember that the area of a triangle, let me write area since I forget one of the points is A, is going to be 1/2. Now pick any two of the sides, so we'll write them as vectors. Side AB cross, let's go with side BC. And then we need that to be a magnitude so that we get a number out of this. Vector AB is equal to 3 minus a negative 1 is 4. Negative 2 minus 0 is negative 2. And 0 minus 1 is negative 1. Vector BC looks like 4 minus 3 is 1. 1 minus a negative 2 is 3. Negative 2 minus 0 is negative 2. Doesn't matter which two sides. This is for any triangle, not just a right triangle, so we don't have to worry about the legs. We just pick any two sides. Now let's do the cross product. AB cross BC is the determinant. I, J, K, and let's put 4, negative 2, negative 1, 1, 3, negative 2. So, as the 2 by 2's, it would look like negative 2, 3, negative 1, negative 2, I, minus, let's see, for J we'd have 4, 1, negative 2, J, plus 4, negative 2, 1, 3, K. And so we're going to get 4 minus a negative 3 minus negative 8 minus a negative 1 plus 12 minus a negative 2. So I get 7I plus 7J plus 14K. And then by the formula, the area is 1/2 the magnitude of that. So the magnitude will have 7 squared plus 7 squared plus 14 squared. And so we'll just blow off the getting the number. That's the area of that triangle. I always like to play this fun game of scalar, vector, or not possible. And so let's try that here. Remember that the cross product gives you a vector and a dot product gives you a scalar. So let's see what happens here, starting with what's in the parentheses. Here, V dot W is a scalar. And so here I'm asked to take a vector and cross it with a scalar. Well, can't do that because a cross product is between two vectors. So this one is not possible. In the parentheses in problem 2, the cross product gives you a vector. So I can take the dot product between a vector and a vector. And when we do that, we get a scalar. In the next one, I've got the cross product between two vectors we know is a vector. And then if we take a cross product between that and another vector, by gosh, we get a vector. For the next one, we've got a dot product between two vectors, and that's a scalar. And now this dot is not a dot product anymore. It would be scalar multiplication of a vector. So if we think of this as times, then scalar times a vector is a vector. But if we think of this as the operation dot product, then we'll have to say this is not possible, because the dot product is between two vectors. But if I wrote this, U times V dot W, then this is going to be a vector, because this is a scalar multiple of vector V. Number 5, U cross V is a vector. U cross W is a vector. And now we're going to dot a vector with a vector, and we'll get a scalar. Didn't I tell you this game was fun? All right, let's see. U cross V is a vector. U cross W is a vector. Now vector cross vector is a vector. The single bars here means absolute value. So if this has a chance of being anything, it's going to be a scalar. Let's see if these operations are allowed. U cross V is a vector, and now W is a vector. The dot product is a scalar. The absolute value of a scalar is a scalar. The 2 bars means magnitude. So again, if the stuff inside the magnitude symbol is a vector, then the magnitude is going to be a number. So we check U cross V is a vector. Cross with another vector is a vector. The magnitude of a vector is a scalar. All right, that's all I was going to say. You'll see cross products in physics applications. One application maybe you've already done in some physics classes is torque. If you revolve a gear or a wheel, then the torque is a pull in a certain direction. We'll use the cross product in Calculus 3 many times. So get a hang of calculating them, and when you start your calculus,